Dr. Perrotta and UC Merced. I'm going to be doing a mechanism video. This time it is the aldol condensation between this ketone derivative and this other ketone, double barrel diketone derivative. The reason this one has no alpha protons and this one does have alpha protons at both the two alpha sites. And that's going to give you the alpha beta unsaturated dicarbonyl. Saturated carbonyl compound. Whenever you do an aldol condensation, you get the alpha beta unsaturated carbonyl compound. So in this case, the first couple of steps will be very much similar in both cases. So this one's going to be a little bit lengthy because of the process. So you're going to treat this with sodium methoxide and methanol and heat, and that's what's going to cause the condensation reaction. So in the first step, what will happen is you're going to get a deprotonation of the alpha site, and the alpha site of one of them, I'm going to just choose that one with the methoxide anion. And so you're going to form the enolate, and there's different resonance structures that you can form from the enolate. I'm going to choose to just go directly to the enolate, but you can obviously draw different resonance structures for it. So of course it's an equilibrium, and you're going to generate more methanol as the byproduct and generate your enolate that you're going to use as your nucleophile with this electrophile right here. So that electrophile has no alpha proton, so that makes the aldol condensation or even an aldol reaction much more facile. So we're going to then add in our electrophile. So at that point, our electrophile will be then attacked at the carbonyl carbon. So I'm going to choose to attack at this carbonyl carbon over here, but it's completely symmetrical, so it really doesn't matter which one I decide to effectively attack. So one of these lone pairs on here will come down, and the double bond or the alpha carbon will attack at the carbonyl site and then kick up the electrons onto the oxygen atom. So of course that's another equilibrium process, so you're going to get something that looks like this. So now you regenerate your carbonyl, and now you've effectively added one of these groups. So you've made this bond right here, and that will generate this as an intermediate. So you still have the other carbonyl still attached, like so. And so at this point you're going to protonate. So our protic solvent that we used is methanol. So you're going to protonate using methanol. So this guy will then protonate. So to give you your neutral intermediate. So this will give you this intermediate like this. And it's an OH here, and phenyl, and now you've got your other phenyl ring here and a double bond. So at that point, you're going to then proceed in the next step, because you've protonated using methanol to give you more methoxide anion. So that's why it's buffered, is so that way you regenerates more methoxide each time. So in any aldol condensation, you want to look for this as a key intermediate, just like when we did before in previous cases with that of enamines or imines and that of different acetals. This is our key intermediate in any aldol condensation. Is actually the aldol product. So this guy's the aldol product, and that's why the reason is because you've got an alpha and a beta hydroxy ketone compound. So each time, if you go through this, you're on the right track. So from the aldol product, you're going to do a elimination of the hydroxy group. And it's going to look weird because we've never really seen hydroxide anion as being a very good leaving group. But in this case, it is going to be a good leaving group. So I'm going to redraw that beta hydroxy carbonyl compound over here. So from the beta hydroxycarbonyl compound, what's going to happen is what's called an E1CB reaction. And the E1CB is the elimination first order. And what's going to happen is the following. So your methoxide anion will deprotonate at the alpha site. And you can draw several resonance forms. I'm going to draw one of the resonance forms of this, which is the enolate anion. So here's our methoxide anion, and it's going to deprotonate this hydrogen and going to give an enolate, or you can draw it as the carbanion, whichever you like. I'm going to draw it as the enolate. So that's just the conjugate base of this guy. So then that, let me fix this arrow here. I'm a little bit off track. So this arrow is going to go to this, make a double bond. And so at that point, what you're going to get is this enolate, like this. And it's going to turn out that our E1CB process will be exactly the same when we do it the second time we do the aldol condensation again. So then that would give us this intermediate, which looks like this. And now what we can do is push out this hydroxide group because we formed a stable enolate. And what drives this is actually the conjugation that you gain after dehydration or loss of hydroxide or water. So in this case, you're going to get plus methanol is the byproduct. And so since you're in basic conditions, you're allowed to remove hydroxide anion because you're under basic conditions, because that makes just more base. So from the enolate, or from the carbanion, I'm going to choose the enolate, you're going to reform the carbonyl, and at the same time, this double bond will push over to the beta site. And so if we just label this as alpha and the beta, I'm going to stop doing that in a second. Then you're going to actually cleave this oxygen-carbon bond to form a double bond there. So then that will give you this product. So in this sense, this is a little bit irreversible in all the aldol type condensation. So you're going to get this as the product initially, like so. And then you're going to have this plus hydroxide minus. So it's okay to do this. This process going from here to there is called an E1 elimination 1 conjugate base, E1CB. So it's a conjugate base, kind of a special E1 case. So it's E1 because you just don't eliminate it all in one step. You wait for the conjugate base to be formed. It's a real thing. You form the conjugate base, the enolate or the carbanion, and then you push out the hydroxide as the leaving group. And this goes same with the acidic conditions, in which case you would protonate the OH group, but we're not under acidic conditions, we're under basic conditions. So that generates more base in the form of hydroxide. So we're going to deprotonate this guy again using sodium methoxide. So I told you it's going to be another repeat. So you're going to deprotonate this hydrogen right here. And I'm going to draw the enolate right away. And that enolate is going to look like this. So now we're going to form enolate on the other side. And the reason we can do it on the other side is because of the fact that this side of the carbonyl has no more alpha protons. So we'd have to draw it where it forms the enolate on this side. And also you can look at what your product is to help you out in terms of what could be possibly happening in your mechanism. So whenever you're going to get stuck in your mechanism, you always want to think about what your product is, just like you do in a synthesis problem. So now you got your enolate, and your enolate will then collapse down to then attack this carbonyl, like so. And that would then create an oxygen minus. And the oxygen minus will then get protonated, and then we're going to do the E1CB again. So at that point, you're going to get oxygen minus, so something like this. So now you've effectively added another group at the alpha carbon and made this bond. So you're going to get an O minus like this and phenyl. And so you're almost at the beta hydroxy carbonyl compound. And we couldn't have deprotonated there because you have a double bond and no hydrogens. So that was the only site in which to deprotonate can occur. So at that point, you're going to get plus methanol because you deprotonated initially over here. So I forgot to write at this point, you also have plus methanol. So you regenerate your methanol. So that's what you're going to use to protonate over here. So we're cycling between methoxide ion and methanol. So at that point, you're going to protonate just like we did before. So then that'll give us this intermediate, like this. This up a little bit. So you're going to get this intermediate where it's OH and phenyl. And now we can proceed to do your E1CB reaction because now you've got your beta hydroxy carbonyl compound. And this is your aldol product again. So whenever you're doing aldol product within an aldol condensation, you would stop at your aldol product, which is your alpha beta hydroxy carbonyl compound. So now we're going to proceed with the E1CB because we've regenerated more methoxide anion. And from the methoxide anion, we can proceed, like I said, to the E1CB and finish this off. So I know it's a lengthy sort of mechanism, but at this point, it's just fairly straightforward. We're just going to repeat what we did earlier. So the methoxide anion will deprotonate this hydrogen. This time I'll draw it as the carbanion, but you can draw it as the enolate, which would be perfectly fine. They're just resonance structures of one another. And you have your hydroxide here as your poor leaving group, but under these kind of conditions you can get it to eliminate because you're under basic conditions. And so you regenerate more methoxide. Sure, you can probably pre-protonate that carbanion, but at this point, to get you towards the product, the carbanion will then form a double bond and kick out the hydroxide group. So you're going to generate more hydroxide ion and get to your final product, which is this alpha beta unsaturated carbonyl compound, which is your final product here. So at this point, that's what I was saying in terms of the mechanism. It's very similar. So this step right here is your E1CB again. So you're going to do the E1CB again to generate hydroxide and your final ketone, alpha beta unsaturated ketone product. Okay, so that's it for this aldol condensation video. It's a double aldol condensation. It's a good one to do because it is an intermolecular process.